cover exponential growth and decay problems. The last class, we went over how exponential growth functions. Exponential growth is represented by exponential functions that are increasing, right? Something that looks like that. And of course, exponential decay will be represented by a function which is decreasing, maybe something like this. Okay, now what we're going to do is look at some problems where we're going to use exponential growth and decay. And just to review, remember what makes a function exponential is that the independent variable is the exponent, all right? Now, you might be thinking, well, here's another variable and here's another variable. Well, C, it stands for initial amount. And other textbooks, I have not checked what your textbook is using, but I know the pre-cal textbook, instead of using capital C, it uses capital P. Right, Chris? Yeah, for principal. And the principal that, like this, let's just make it clear. That type of principal. Like the money you put in at first, okay? Not the P-L-E.
The rack.
Anyways, we're getting off track again. So in this case, we're going to use the capital C, okay? Now, little r, or lowercase r stands for the rate. And the rate, this time we're going to talk about money problems. So, interest rate, for example, if the interest rate is 20%, or let me tell you this, some credit cards have an interest rate of 26.99. Stay away from those things. Because once you turn 18, you're going to start getting credit offers like crazy. And you're going to be tempted to apply for them. And so, any rate like that is completely going to, like, you're going to end up paying 10 times more as what you should have for an item. Okay, so stay away from things like that. So interest rate, when we use these problems, when we solve these problems, we're always going to consider the interest rate in decimal form. So if my interest rate was 26.99, in decimal form, we move the decimal point 2 units to the left because we're actually dividing by 100. And so it will be 0.06, I'm sorry, oops. It will be 0.2699. Okay, so if you have something like 20%, then as an interest rate, as a decimal, it will be 0.20. All right, now, if your interest rate is 2%, please don't get that confused with 0.20, okay? That it's actually going to be, what would that be, guys? 0.02, okay? So be very careful about those. And one that we always know for sure is 50%, right? Because 50% we know is half, so it's 0.5. So if you're talking about a rate that it is, I'm running out of room here, 6%, which are the most common ones, you know, not maybe rates from like 4 to 12%. That's what you see most, like, with with money. So 6%, what would that be as a decimal, guys? Is it 0.6? 0.06. So please be very aware of that, okay? So that's it. Let's go ahead and start solving a problem. And this one is actually solved for you already, I think. So if I could have a volunteer to read it, please.
In 1995, let's suppose a town named Jackson had a population of 15,500, and it was consistently increasing by 10% per year. If this yearly increase continues, predict the city's population in 2015. Round the nearest hole.
Okay. So, as you notice, right here is telling us the population in year 1995, right? And the population was 15,500. Now, I know the table that you see here, it starts at x equals 1. So, x equals 1 is assigned to the year 1996. So the year 1995, what X value should we assign to? 0, very good. And so that is something that we always have to consider, the starting time, times 0, all right? Or the initial value. So when we talk about, this problem will be about people. When we talk about money, same thing. We always have to consider times 0, all right? So right here, to solve this one, we have that the rate of, and we know it's increasing. So just to go back to this one, our model is going to look like this, right here. We're going to have the initial population, the population during the year 1995. Here we will have our rate, which will be in a decimal, 10%, and then X will represent the number of years. Since we are increasing, we're talking about exponential growth. Right here is saying that we will have a 1 plus the rate. What do you guys think the 1 stands for?
The amount the base amount.
The base amount, right?
Yeah.
So if we were just to multiply it by 0.10, then we're kind of losing what was already there, right? So that's why we have to use that 1. All right, very good. So now the question is, predict the population in the year 2015. So now this is when you got to think of this. If X equals 0 is representing the year 1995, what value of X will be represented by 2015? Is it 20? Okay, do we all agree? Okay, perfect. So now what you're going to do on your, is that a different problem? Oh, that's the same problem. So let's go ahead and construct our model. And so just to keep the same, we're using Y, okay. To keep the same notation, we will use Y equals C times 1 plus R. Okay. We already knew that C is equal to the initial 15,500, and our rate, it is equal to 0.10. Remember, as the decimal. So then we're going to substitute here. Here I'm missing an X, sorry. So we're going to substitute what we have, 15,500 times 1 plus 0.10. And remember, we agreed that the year 2015 was going to be represented by X equals 20. Okay. Now, I know that you might already know how to write this down on the calculator. I mean, type it on the calculator. Okay. But just to make sure we're on the same page. So you go to calculate, and 15,500. You open your parentheses, and that's where you will enter 1 plus 0.10, or you could just enter 1.1. That will be up to you. And then you must exit out of the parentheses, and then you will use the button, the caret symbol, and oh, I didn't take it right there, and then we will enter 20 for the exponent. Oops. What was that again, David? I'm sorry.
I didn't hear it. I can't see what's inside of it. He was asking whether it was 1 plus 0.1.
Oh, yes. Why is the mouse there? Okay. So the 1, remember, that's the one, oops. That's the one accounting for the original amount, and then the 0.1, it will be the same as 0.10, the 10%. You could also enter it this way, 15,500 times 1.1 or 1.10, and then with the exponent 20. It will give you the same. Okay. So let's just check to make sure. There we go. So after 20 years, population. So after 20 years, the population was going to be, could someone help me?
104,276.
104,276. 276. Do we have any decimals?
Most likely not, because you can't really have like half a person.
Oh, okay. We didn't get any. Great. But yes, when we get decimals, exactly, we will have to round up. Correct. In some cases, some problems we might have to round down or up. Okay. Which, if any of you is interested in computer science, there's actually a mathematical function. It's called floor and ceiling, like for round up or down. Okay. All right. So let's move on to the next problem. Now the next one is exponential decay. And so in this case, the difference with the first formula, exponential growth, is this minus right here. Oops. Let me just play the show. So it's this minus. Do you guys see it? Yes? So for exponential growth, we had 1 plus the rate, because it's growing, right? So it makes sense. For decay, you're subtracting that rate, but the 1 is still accounting for the original amount, correct? All right, so same explanation. The independent variable is going to be the exponent. And so let's get to the problem. So who would like to read this problem? Matthew?
A large golf country club holds a singles tournament each year. At the start of the tournament for a particular year, there are 512 players. After each round, half the players are eliminated. How many players remain?
Okay. Now this problem, we could actually solve it, without even a formula. But we're going to do it both ways. Okay? We're going to do it just by intuition, and then we'll do it with the formula. So again, initial amount right here, Matthew is telling me 512. So that goes here. It kind of bothers me that they don't include it, like at the beginning. Okay, so when the independent variable is x, is 512. Then it says every round it cuts by half. So half of 512 is, I don't even need to do that. It is 526. Half of 512 is 256. Then half of 256 is 128. Half of 128 is 64. Half of 64 is 32. So you guys know what the next numbers will be, right? What will be next? 16. And then 8. And then 4. And then 2. And then they will have the winner, right? So the problem says, what is going to happen after 6 rounds? So I think we could figure it out here. This will be the 5th round, 6th round, 7th round, 8th round, 9th round, right? So the 6th round, we're going to have those many. So now let's do it with the equation, see if we get the same thing. So what do you guys think the decaying rate will be? The rate. 0.5, right? Because half is 0.5. If we were talking about percentage, it will be 50%. So 50% of the players are cut off every round. Does anyone play golf here?
What?
The real kind? No, I'm not really familiar with the rules of any
It's
sport.
just like any.
Well, all I can tell you is that if
Lowest
you get
score.
like negative 20 points, you're definitely gonna win.
Oh, okay. All right, so let's go back to our original model for exponential decay, which goes initial amount times 1 minus the rate to the power x. So we started with the original initial amount, 512. And then we had the rate, it is 0.5 for 50% or for half. So now let's substitute and we will have the initial times 1 minus 0.5. And then we want to know after 6 rounds, so we will make our exponent equal to 6. So if you guys could please enter that on your calculator just to verify that we get the same number. Yes, what was the number? I forgot this. 8. Okay. Now, of course, for this particular problem, it was very easy for us to do that, right? To just kind of like keep taking halves, halves, halves. Sometimes that is not so easy, or it could be easy but time consuming. So that's why we have to rely on the equations, right? That's why we have to learn how to create them. So let's do one more. Is that the last problem we have?
Yes, it is.
All right. So after this problem, we'll go take a break. All right. Now, half-life. This is something very important in chemistry, guys. Okay? And so the half-life of a substance is the amount of time it takes for half of the substance to decay. So I'll do my best to explain this to you because you will see it in chemistry. If you're already taking, anyone taking chemistry already? Are you guys in half-life yet or not yet? Okay, you will see it very soon. So I'm glad you're seeing it here first. So, for example, if I give you, if Samantha has 100 grams of gold. I'm not sure what the half-life is of gold.
I can look it up.
Can you look it up? Yes. Oh, I took your phone. Never mind. Look it up, Kat. Just so that we don't tell lies.
I don't think it has a
Every single thing has a half-life.
Just like you did the
I know the half-life of carbon-14, which is the isotope that is used to detect. Okay, you guys know when they discover fossils?
Yeah.
Right? When I was little, I used to be so intrigued by like how do they know how old they are? Like, I don't get it.
They are.
Well, in fact, what they do is they test the amount of carbon-14 that is still remaining in the bones or in whatever artifacts they found. And so, depending on that, they're able to calculate the age. Okay? So, what is the half-life of gold?
There are a lot of numbers on that. Read them all out.
Yours.
Read out the numbers.
Okay, so this is an isotope of gold. Okay, it's not just gold. So it says here 2.697.
You got years?
Days.
It depends on
It depends on the isotope. For example, some elements are able to,
Just flash through.
I don't want to say disappear because matter, you know, it just transforms. So it has the ability to kind of like transform into I don't know what. In days, others it takes seconds, others it takes years, others it takes days. So with carbon-14, it takes years. There are others that will just like half of it will disappear. So I'm just gonna make one up. Here we go. Because we don't want to get to I don't want to like contradict the chemistry department. Okay, so let's just pretend that the half-life of gold is gonna be 50 years. So then when Sam gives that 100 grams of gold to her great-granddaughter 50 years after, she's actually just going to have half of that, 50 grams, after this many years. So that is what it means, okay? Let me do one with carbon, because I am more familiar with that. Let me give you an example of carbon. So let's say that certain thing has 2,720 grams of carbon-14. So the half-life is 5,217 years. Or it could be 5,712. Sometimes I mix the two. So what will happen after this many years is that this amount is going to be cut into half. Okay, so I'm going to need you guys to help me. What will be half of that? What's half of 27? Okay, so it will be 1, 3, 6, 0. Yeah, is that what you will say? Thank you very much. So after this many years, it will be that much. Now, what do you guys think will happen after another 5,217 years? What do you guys think the amount will be?
680.
680, correct. Very good. Okay. What is it? Just, okay. All right. Bye. You're welcome. Samantha Ramirez to the office just to pick up something. Do you guys think this amount will never be zero?
Most
There
likely
will be
not.
a day.
No, actually, there cannot be a single day there it can be zero because if you split everything in half, it still cannot turn it to zero.
Yeah. So every 5,217 years, that will go to half. So then it will be 340. And then what? 170. And so on. It will never be zero. It will get to like 0.000000009. Yeah? So that's why they're able to calculate the age of such like old artifacts or fossils or bones or whatever they are. Okay? So this one right now, like I was saying, every element has a half-life. And so when you are in chemistry, you will use this. So this is one of those things like when you ask me, when are we going to use this in life? I can tell you in chemistry class. But of course, you know, there are several fields where half-life is actually quite important. All right, so in this case, we have a form of pesticide, DDT. It was actually banned in 1972, although the Army kept using it. My uniforms were actually sprayed with that one. And we're talking, you can tell us in a sec, we're talking about, what year was that? 2003, yeah, my uniforms were sprayed with that.
How did it smell?
Tell us why they were banned.
Because instead of just killing pests, it killed everything.
Yeah, and so they're actually highly toxic. My anatomy professor says that anything you put on your skin, like you should just stop immediately, including lotion, because it penetrates your germs. So I've been using coconut oil since he told us. All right, going back to this. So the half-life of this pesticide is approximately 15 years. Okay? If a storage unit had 400 pounds of DDT, so again here, at time 0, there were 400 pounds, okay, of DDT. Find how much DDT is remaining after 72 years.
None, because the cup's gone.
After, what year will it be? 72, that's true. I wonder if it's banned in the whole world. I wouldn't think so.
Chemical warfare.
I know what one chemical is banned in.
You know, it's
Everything. Agent Orange.
All right, so let's go ahead and create our equation. Now, do you guys notice that we don't have a percentage, right? We don't have a decreasing rate. However, we do have half-life, and we have 15 years. So right there is where we're going to create our percentage, okay, our equation. So let's see. What was the initial amount, guys? I forgot.
Yes.
400, okay. 400 pounds. And that was at x equals 0, right?
Yes.
Okay. Now, at time, what is the half-life? How many years?
15 years.
15 years.
About.
So it will be half of the original, right? So what will be the amount then? The final amount will be 200. Not C, let's color Y. Like that. So what we're going to do is we're going to find R. We're going to find the rate. Right? So we're going to create this, and I'm going to use the original model, which is Y equals C times 1. It's decaying, right? It's half-life. It's half-life, we're talking about exponential decay minus R to the power X. So now, what I'm going to do is I'm going to substitute this Y, this C, and this X. You guys do that? Substitute with what we have here. 15, 200 for Y, and 400 for C. So that it looks like this. All right. Now we gotta solve for this R right here. So let's see what we can do. If we just consider everything in parentheses and the 400, what's the 400 doing to the stuff in parentheses? Multiply. So we gotta divide, right? Because that's the inverse operation. So we do that, and of course you already know what we're going to get. We're gonna get 1/2, right? Or we're gonna get 0.5. Okay. Good. Now this question right here on this solution, they're asking us to do kind of like an estimation thing. Now I'm not a very big fan of estimating. In fact, I hate when my son gets homework like round to the nearest whatever. I'm like, no, math is exact. Why are you asking me to round? I can't do that. So this equation right here, we cannot solve it anymore unless we use the inverse of an exponential, which is the logarithmic function, all right? So after we cover a little bit of the next packet, which is logarithmic functions, we're going to come back to this and we're going to solve it, all right? So right now, this will be the end of this video. This was the last problem? Yes? Okay, so we're going to stop here. Let's take a break, and then we'll get started with logarithms. Bye!